excited to be able to come here. I really wanted to come here first after the announcement, as my new home that I'll be here soon. So I'm really excited that you all are here and excited too. So so before I start, I wanted to emphasize, this was a huge team effort, and I know, right now in the media, there's a lot of stuff going around that, I single-handedly, led this project. That is as far from the truth as possible. So I just want to make sure that everyone knows from the beginning that this is the effort of lots and lots of people for many years. So anyway, okay. So if you, oh yeah, maybe that'd be good. Oh, I also want to say I've been busier than I thought the last 2 days, so this might be a little bit more casual speaking than I would have hoped. But okay, so if you go out, in the tonight, you might see the Virgo constellation, and if you zoom in towards the head of Virgo, there's actually this giant elliptical galaxy called M87, and it's 55 million light years away. And if we could zoom in very far towards the center of M87 with a radio telescope, we would see these flailing arms of a jet. And what this jet tells us is that at the heart of it, there's what is a supermassive black hole. So a place where once too close, nothing can escape, not even light. And although we have never been able to see this black hole before, we see the effects of it in the jet. And what we are trying to do in the Event Horizon Telescope is see something as small as that little dot there. We've been trying to image the core of the black hole, the immediate surrounding around that black hole. And if we believe that if we were to zoom in, we would see light that was zipping around and bending due to the immense gravitational pull of the black hole. So if Einstein was right about general relativity, this light would bend itself into a ring, in which case, where you would have a dark spot in the center. And the brightest area of the ring is called the photon ring, where you have photons that are basically orbiting near continuous orbits. But anyway, this black area here is called the black hole shadow. This is what is referred to as the black hole shadow. And simulations of the turbulent, in that black hole shadow tells us about general relativity through its size and its shape. And so we'd expect for certain spins and masses that would define what that black hole shadow looks like. So simulations of turbulent plasma in the jets and accretion disk around the black hole predict that we would see this kind of infinite resolution image you kind of see here, where the gas is just flowing around, but you have this bright ring, the center. And so, in 2017, we hooked up an Earth-sized telescope, and 2 years later, we produced this image of the black hole in M87. So we were really excited to be able to show these results on Wednesday. And today I want to tell you more kind of all about the experience of making that first image of the black hole, what makes it so hard, what did we do how do we reconstruct it, how did we verify what we reconstructed, and also what did we learn. Okay, so the question of what makes it hard, maybe if you think about Hubble, you think this is a really high resolution image. But M87 is a galaxy 55 million light years away from us. It's so small that even Hubble, it barely can see that jet, that big booming jet that's like galactic scale. And so people have been trying to zoom into M87 for many, many years. But seeing a shadow requires that we have a really particular kind of telescope with the right size and the right observing wavelength. So for long radio wavelengths, you can't, for short radio wavelengths, you can't get down to that event horizon. And also, if you have too long of a radio wavelength, you can't get down because the gas around it is optically thick. So for instance, here is a 3 millimeter simulation of, a simulation of what you would see at 3 millimeters. And as you continue to go down, reducing the wavelength to around 1 millimeter, this gas around it sheds off, and you are left with this ring of this event horizon that we would expect to see. And this ring is really, really small. So it's about 40 micro arc seconds in size, which is about the same size as if you were trying to take a picture of an orange on the moon. And just to put it in Hubble terms, here is a 1 pixel square of Hubble, and here it's going to show you what the size of the image that we created is. So it started with 1 pixel of the Hubble telescope, and it zooms down to what we see. This is credit of Alex Park. Anyway, so if we plug this wavelength and required angular resolution into our equations of diffraction, you can just easily plug this in and you can see, okay, the telescope size that we would need is the size of the entire Earth. And so if we could build an Earth-sized telescope, we could just start to make out this really distinctive ring of light that's indicative of the black hole's event horizon. But building a single-dish telescope the size of the Earth, isn't possible. And so by joining telescopes from around the world, I've been working as part of this international collaboration called the Event Horizon Telescope, which has built a computational telescope the size of the Earth, and it's the first one capable of resolving structure on the scale of a black hole's event horizon. And so joining telescopes in this manner is a term called very long baseline interferometry. And in VLBI, or very long baseline interferometry, all the telescopes in the worldwide network kind of work together. They're linked through the precise timing of atomic clocks. And so teams of researchers at each of the sites basically freeze light by recording petabytes of data. And then we shipped all this data together, and the computers process the data together to act like a big Earth-sized lens to make the picture. But how do we actually make a picture from disjoint telescopes like this? Well, unlike with a regular camera, in VLBI we don't actually capture a picture in pixel space, but instead in frequency space. So we essentially take measurements of the black hole images Fourier transform. And if we put telescopes all over the globe, everywhere, we would sample every point on this Fourier transform, and then it would be very easy to make an image. But since we only have telescopes at a few locations, we only get a sparse number of measurements. And it turns out that for every 2 telescopes in our telescope array, we get a single measurement that's related to the 2D spatial frequency between the telescopes. And so the closer that 2 telescopes are together, the shorter the spatial frequency, the smaller spatial frequency is, and so we're going to measure large spatial structures. And so to measure that fine detail, you need to see that precise ring. We need to put our telescopes really far apart. But with the EHT only actually has 8 telescopes that we observed in 2017 with at 6 different locations. So that's actually only 6 choose 2, 15 distinct frequencies that we can measure at every time. And that's pretty small number, but fortunately, as the Earth rotates, we obtain other new measurements. So since the baselines between those telescopes change as the Earth rotates, this amounts to carving out different elliptical paths in the frequency plane. And this is the UV coverage that we had for this in the 2017 observation of M87 for one of the nights. Okay, so, well, how do we even get these measurements? I mean, basically, we have this tiny, tiny little signal riding on a huge amount of noise. And so we get it first by recording hundreds of terabytes of data at each of the telescope sites. So much data that we actually have to fly it back to a common location, which is very hard when we're collecting data at the South Pole and we have to wait for their winter to be over. So then at that common location, we use this special purpose supercomputer called a correlator, which combines the data using the precise timing from those atomic clocks. So we make sure, because we really need to know that time delay between the signals. And once this is done, this is then passed on to a calibration stage, which tries to find a weak signal hidden in that correlated output by solving for things like the absolute phase of a single telescope over time. And this is able to turn this weak signal into a stronger signal. And developing this calibration pipeline was very unique. Like, although these ideas have been around for a while, developing it for the short millimeter wavelengths that we had to work with for the EHT was a huge project. And I just want to call out Lindy Blackburn, who really spearheaded this, and also Maciek, Sarah, and Michael, who also were really instrumental in getting this part working. If it wasn't for this, we would have no data to make images from. So at this point, we have the data, and then we can abstract away basically all the astrophysics of the problem and kind of just think of it as a purely computational imaging problem. We have these sparse, noisy data, and our challenge is to find the image that actually caused it. You know, and as I said, if we had measurements everywhere, if we had telescopes all over the globe, we would sample every point in that frequency plane, and this problem would be really trivial. You would just simply need to apply the inverse Fourier transform in the case that the data wasn't noisy. But because we only have a few samples, that means that there's actually an infinite number of possible images that are perfectly consistent with the data that we do measure. And so how do we actually deal with this? Well, the traditional method that has been around since, really since the 70s is a method called clean. And clean kind of works by assuming that the data isn't really sparse, and it puts a zero kind of everywhere where we haven't observed data. And then by simply applying the inverse Fourier transform on these measurements, the method obtains then a very noisy, artifact-heavy reconstruction that doesn't really look like the original image at all, but it kind of has somewhat the same shape. But at this point, then the method kind of throws away the data, and it says, oh, how do I clean up this image? And it does that by assuming that the underlying source is just a bunch of point sources. And so it iteratively searches for the brightest point in the image and then removes the artifacts that would occur due to incomplete sampling in the frequency domain. And then this image, after you found all these point sources, is then blurred to merge the points into an extended source. So as I mentioned, this is kind of the default method that's used to solve these problems. And this method actually works really pretty well out of the box when there are a lot of telescopes and when you're observing at longer wavelengths where you can really calibrate your data. But for the short wavelengths that the Event Horizon Telescope operates at, and for the small number of telescopes it can use, this method starts breaking down. And the reason, I guess the method, in the cleanest sense, I guess, starts breaking down. And the reason why, there's a couple reasons. And one of the primary ones is due to the atmosphere. So the reason VLBI is able to work in the first place is due to the fact that light from a black hole, you know, it's going to travel 55 million years, and then it's going to reach the Earth as a plane wave, and it's going to reach one of the telescopes slightly before the other one. And this time delay is really key for extracting that 2D spatial frequency measurement that we use for imaging. But however, the atmosphere causes random delays in each of the signals, which leads to an a completely random phase in our measurements. So in addition to that, the atmosphere also causes different attenuation factors in the signal. I mean, you're going to have different kinds of cloud cover above Hawaii than over Chile. And so you're going to have a different attenuation. So you also are going to have a different absolute gain term. And on top of all of that, the measurement function that we have can also have problems with these gains due to things such as pointing errors, being out of focus, having astigmatisms, or just problems with the electronics. And it turns out that for the EHT, these were actually particularly a problem at the LMT, which unfortunately I was at. But this telescope was observing actually while it was still being commissioned. It wasn't completed yet. And so there were a lot of things that on a regular telescope that you have to allow yourself to, for instance, point your telescope. And instead of what we had to do is we kind of had to come up with things on the spot. So what we did instead is we just raster scanned the telescope every time we wanted to try to point. We just raster scanned the telescope, and we get these terrible total power signals. And then we have to figure out, okay, in this image, where is the source? And it's pretty bad. Anyway, so we came up with this match filtering algorithm that allowed us to do this. And we did it, and we were able to point fairly well on a lot of the sources, but for a source as weak as M87, it was really a problem. And so we had pretty terrible pointing, and as we found out later on, the gains of our telescopes were really bad. So the gains should be pretty close to 1, just jittering around 1, and for the LMT, they were just like off by like almost 100% sometimes. So it was a big challenge to deal with this data. Okay, so for all of these problems, the errors turned out to be kind of bad. I mean, if you look at it, it looks like we have no phase information and no amplitude information. So like, what are you supposed to do, I guess? But but actually, and if you try to do something with that, and you try just to take that inverse Fourier transform, remember before it looked somewhat like, in the simulated example, somewhat like the image on top. But here it's just all scrambled, so it's very hard to figure out what to do. But if you notice, actually, these individual terms, the phis and the gains g here, actually are station-based, while our measurements are pair-based. So for instance, if we had added a third telescope, then we would share between that third telescope and the second telescope some of those same gain and phase terms. And so that allows us to solve basically for a smaller set of calibration terms, basically during our imaging. And so we've had to develop two classes of algorithms that we then explored in our work in order to deal with this, these particularly bad calibration errors. And I'm not going to actually go into the details of these, but I'm going to just give you the flavor of them. So the first is inverse modeling, which is based upon the clean algorithm that I talked about. And we really wanted to, so anyway, so it basically, in this clean algorithm, it works as I said, except you can't do the clean algorithm normally when you have all these crazy phases and gains. So what they do instead is you solve for an image, and then you fix that image, and you solve for the gains and your calibration terms that would best fit your current image, and then you iterate back and forth. And this is really a good algorithm for us to have used because, for I guess a couple reasons, but mostly I think because it is the traditional algorithm that is used in radio interferometry, and we needed to make sure that just because we came up with new methods, that older methods would still be able to get the same thing. But a disadvantage of this method is because it is really this solving for an image and then solving and then fixing that. It can get really stuck in local minima, and so it has a lot of guidance from knowledgeable users. And for instance, I think I skipped it, but actually you usually have users put down little boxes called clean boxes of where you're going to put the flux in. So it's guided a lot by the human, the user who is running the algorithm. And so a second approach in methods is something we've been developing more recently. And I've been doing this primarily with, there's a number of people, but primarily with Michael Johnson, Andrew Shale, and Kazuo Akiyama. And we've been developing methods that take a more Bayesian-inspired kind of approach to the optimization problem. So in this problem, we're not just trying to find some sort of inverse function that takes us directly to the measurements, but instead we try to find a picture that both fits the measurements and is likely under some kind of described function of what is a likely image. And so and then we kind of use some sort of gradient descent approach to solve for the image. So the disadvantage here is that we have to define what is a likely image. We have to impose some sort of information that can bias our image, just like how the human could bias it in the clean method. But the really big advantage of this method is that we can incorporate other types of ways. We can incorporate these different types of errors that we'd expect in our likelihood term. And we do this in a couple ways, but the main way that we do it is by incorporating what are called closure quantities. And these are quantities that are actually invariant to these calibration terms. So in a closure phase, you actually, if you take 3 telescopes in a closed loop and you multiply the visibilities, so these complex visibilities, you're going to add their phases, and these additional effects to the atmosphere actually cancel out completely, and you're left with a term that is the same as if you didn't have any atmosphere. And similarly, in something called a closure amplitude, if we multiply and divide the measurements of 4 telescopes in a certain order, we obtain a term where the gains cancel out completely, and we're left with a term as if the gains were all 1. So in both of these closure quantities, these were not developed in the last couple of years. They've been around for a while, but they were always around mostly for calibration purposes. So when you're calibrating the data before imaging. And here, rather, that we try to put these directly in the imaging process, so we do calibration at the same time as imaging. And so what you can do is have methods where you don't need any calibration whatsoever, and you can still get pretty good results. So here on the bottom, I'm showing, at the top is the truth image, and this is simulated data as we're increasing the amount of amplitude error. And you can see here, it's hard to see, but it breaks down once you add too much gain error. But if we use just closure quantities, we're invariant to that. So that's really actually been a really huge step for the project because we have such bad gains. Yeah, so, but so here I've kind of trying to give a glimpse of what we do for methods. But I think one of the most interesting parts of this project is how do we make sure we're not biasing our images too much. We have this really sparse, really noisy data. We have to inject something into the problem. We don't want to inject something that's just getting us back at what we expect to see. So how have we kind of gone about verifying the images that we have? And an old technique that I had talked about is a while ago is that you could take many different types of images, and every different kind of image has its own statistical properties. And so one idea is, okay, well, we don't know what a black hole necessarily looks like. So let's impose the properties, the image properties of many different kinds of images, and see if we change the type of image that we assume, if that actually changes the image that we reconstruct. And this was done by splitting up images into little patches and imposing the statistics of those patches on the reconstructions. And what we found is that if we had enough data, it didn't matter really what kind of image. You could have all images of dogs or all images of buildings. It didn't, or all images of things from Hubble's. And it didn't matter. You could get the same image if you had enough data. So this was an idea that we kind of pushed forward, not through having the patches, but by saying, okay, let's try to figure out, can we impose lots of different kinds of image assumptions, impose lots of different kinds of users, and make sure that when they're all independently done, we still get the same images in the end. And so we did this through a 4-step process. First is through synthetic data tests, then blind imaging, then objectively choosing imaging parameters without humans in the loop, and then the additional validation of the images. So the first step was synthetic data tests. So usually in VLBI, we actually had to develop simulation software to realistically simulate what measurements from the EHT would look like with all their different kinds of crazy noise in them. And this is typically, typically it hasn't been done before. So but doing this actually helped us improve our methods a lot. So we did this in a number of different ways. But one of the ways that we found was incredibly helpful was through the Event Horizon Telescope imaging challenges. And these imaging challenges allowed a way for methods to blindly test themselves on synthetic data to make sure that they could reconstruct things even though they didn't know what the true image was. So this was an organized effort in the collaboration. And what we did is we had a set of people choose some sort of truth image and generate measurements from our software. And then we passed this off to the set of these imaging teams. And each of those teams would produce whatever they thought was their best image. And they could use whatever software they wanted or whatever. And then these would be passed off to a set of experts that would look at the images and try to decide, okay, what are the common features? What do I believe? What don't I believe? And do we trust the images that we're getting? And then the advantage of also having the simulated software is that we could also look at the true image in the end too. And we were able to really, as I said, improve our methods a lot. And I just want to show you, though, an example of how we found this was very useful. Not just for improving our methods, but for understanding our results. So here was a result of one of the imaging challenges. At the top is the truth image that at the time when people were reconstructing data, they didn't know what that truth image looked like at all. And here were 5 methods. And so here were 5 methods. And basically, from looking at this, we realized you could try to figure out what was a feature that you believed and what was a feature you don't believe. So for instance, you kind of had this crescent feature in all of these images, but this tail was not in all of them. So maybe you are less confident about a feature like that. And this is what we found people would find, how we would find artifacts. Another thing we did is we also tested on random things. Some people got mad at me about this one, but thinking it's a binary black hole or something. So And the reason we want to do this is we wanted to make sure we could see something that's like completely unexpected. You know, in the last one, people are kind of expecting you're going to get this ringy structure, but you throw something crazy at them and see what happens. And it was really nice to see that all the methods, you know, although some are better than others, they all kind of recovered the structure and didn't recover just a black hole shadow. Okay, so based upon these synthetic data tests, we kind of developed how we were going to approach the M87 data. So we wanted to avoid shared human bias, kind of like how we had done in these imaging challenges, in order to assess common features among independent reconstructions. And the way we did this is that we split up our big effort of people who develop methods, who are knowledgeable users of methods. We split us, and there were about 40 of us who either develop or are good at using these methods. And we split them up into 4 teams. 2 teams which had a focus more on regularized maximum likelihood methods, and 2 on those more traditional methods. Although any team could use whatever methods they wanted. And then we split and then we also made sure that we had people from different parts of the globe interacting with one another. So this was really, truly an international effort. And what we decided is, okay, we want to make sure that when we image, we don't want to just image one time and then all compare our images. We want to be able to make sure that we're ready to compare, that we all are, before we show it, we know that we've actually fit the data. And so we developed also a website that allowed people to submit their images, and then it would provide a set of diagnostics that we could then compare without actually seeing the images. And this proved quite helpful. We actually tested this all out before we even got to M87. We kept the data separated from us, and we worked on AGN, so active galactic nuclei, and making sure that this procedure worked. Something that didn't look even, you can see the image here a little bit, doesn't look anything like that shadow, and we tested that this procedure would work and that we would all converge on the same image in this way. So then after working and practicing for a while, we wanted to make sure we were pretty good at this. In the June of 2018, the M87 data was released, and I remember it because it was my birthday, and I was really excited. That's the first day I saw it, I guess. But okay, so, and at this point, we were actually working with an engineering release of the data, but it was really nice. It was like amazing. I just remember seeing it because you see this jump, which if you know what a circle looks like in the Fourier transform, it's a Bessel function. And that was pretty amazing to see. So anyway, we got this data, and then we said, okay, everyone go into your separate rooms, don't speak to each other, and for 7 weeks, a month, we worked in teams where we weren't allowed to speak to anybody else. And this is the result. So I remember just running into the room, and we all pressed go on our laptops at the same time. We had prepared our scripts so that no one person would get the image first. And as we all watched the images appear on our screen, it was really amazing. And this is what we produced in Team 1, which is the team I was in, at the end of the first day. And then, that wasn't enough. We wanted to make sure, where are those bright spots appearing, all this kind of stuff. So we worked for, 7 weeks, more than a month. And then after that amount of time, we all got together at a workshop in Cambridge, Massachusetts. And once we felt like we were confident to show each other our images, we all showed them at the same time, and it was a really fun moment. And this is what they all looked like. So this was, I think, the happiest moment I've had in the collaboration so far, because I didn't know, you don't know when you're reconstructing. There's so many things that are going wrong. And we were also working with the engineering release of the data at the time. And just because you get something, you want to make sure that everyone is going to get the exact same feature. And although all the images look different, they all have this common feature. It's a little hard to see on this projector, but they're all about a 40 microarcsecond ring that's brighter on the bottom than the top. And that was really exciting to see. And this is that first day we saw them all, the average of all those images together. So even though we had done this and we had done this whole blind imaging procedure, that didn't mean that we still didn't have some sort of human bias in it. Where did it go? Oh, I guess it disappeared. So, so just because we try to avoid shared human bias doesn't mean that we weren't all thinking, we want to see a ring. let's make a ring out of this data. And so then we showed those images at the end of July. And then we spent the next couple of months basically trying to break our images. So the first thing we did is we tried to objectively choose parameters. So in a sense, a very kind of weak kind of machine learning, but we wanted to do it in a way that could be used, that we could do for things like clean, which are completely separate from your traditional machine learning kind of frameworks that we have today. And so we developed 3 different pipelines, imaging pipelines based upon 3 different software. DiffMath is a very old software that was developed primarily around this clean imaging. And then EHT imaging and Smiley were 2 libraries written in Python that were developed recently specifically to handle the challenges for the EHT. And in each of these, we chose a set of parameters that we basically wanted to solve for. What is the best regularizer weight, or what is the best initial Gaussian size? And this is what we tried to do. And we did it by starting with a very small toy data set. But we chose this data set in a certain way. We wanted to make sure that, if you had, for instance, a disk, that if you trained on something like a disk, it wouldn't result. It wouldn't result in a disk. You would still get that hole back in the end and stuff like that. And we chose these. And also we added large-scale structure like that jet to deal with all kinds of other types of error that we also deal with the fact that it's not actually a really compact source. But we chose these models because they all reproduce that dip at the same point. So they all look kind of visually the same in the visibility amplitude domain, not in the phase domain, but yeah. And you can see it looks similar to the true data on the top. And so once we did this, then we came up with a way of training on, then we just tried to train on this data in order to find the best parameters to make those images. So for instance, we took a disk. And so this is not the full procedure, but an example of one, where we took a disk, we generated this synthetic data with all its different types of noise, and then we passed that through the imaging method and saw what came out the other side. And we tried to choose those imaging parameters such that you would best reproduce that image, your normal training setup. But then we transferred these onto the actual M87 data. And what we saw in this case is even though we had trained on a disk and had tried to choose parameters such that it would best produce a disk, that we still got that hole in the center. So it's a nice first test, that we needed that hole to match the data. But in general, we didn't want to just do it on one data set. We did it on a number of these toy data and choosing the parameters that would best reproduce all of them, basically, on the M87 data. And this is what, for example, one algorithm one day, what we would get. And so we solved for one set of imaging parameters for each method that was then applied on all days of data. So we had observed M87 for 4 nights. And you can see every row is the different pipeline, and columns are the days. So you can see how the results look different. It's a little hard to see on here, but I think you can kind of see. Yeah. So basically, all of these look different, right? They all have different assumptions underlying them. But we wanted to say, what is consistent among them? What do we really believe? And so basically what we did is and also if you're not familiar with imaging, you maybe start to overinterpret some features, like things like this, which we know are features that commonly exist. So we wanted to find out, to show everybody, without people overinterpreting things, what can we show them that is believable? And so basically, we blurred them to a level such that they were all consistent to some normalized cross-correlation. And then afterwards, we could average all these together. And that was the image. I don't know if I have it here. Okay, I guess I don't. But the image that we showed. The one at the beginning. Okay, so then once we had these images, then the goal was to try to validate them even further. So remember, the first step of imaging, in the blind imaging, we allowed humans to kind of play their role in making the image, because a lot of times with VLBI data, it's very hard to get something that works right off the bat. We have a lot of problems, the ones I didn't even discuss to you, with bad, you might have bad data and stuff, and so it's hard off the bat. But later on, once the data had been improved, we did this completely, automatically, even for things like diffmap, clean, which normally as a human, like specifically picking locations to put light, we did it completely automatically, and that's one of my proudest things, that I got clean to be automatic. Anyway, so we had a number of validation tests. One is that we had 4 days of data, as I said. So if you independently look at them, you use the same parameters on each day, you can see this ring appears in all of them. So it didn't just appear on one day. It appeared pretty consistently. It appeared consistently across all of them. Okay, so that was a simple one, the easiest one to understand, I guess. But then we also wanted to test, before we were just choosing one set of parameters to show an image. And we called this the fiducial image, because it was kind of arbitrary. But really, there's a whole set of parameters that we think are reasonable. There's not just one reasonable set of parameters. And so what we did is, instead of just solving for one parameter set per method, we tried to solve for a whole set of parameters. And we did that by finding, okay, when we ran our imaging method, if the normalized cross-correlation between the true synthetic data and the data that we reconstruct is larger than that of the true data, and a blurred version, blurred to the resolution of our interferometer, blurred to the resolution of our telescope, then we said, okay, these are acceptable imaging parameters. But if the normalized cross-correlation was worse than that, then it was just reconstructing a bad result. So this allowed us to have a huge number of parameters. Oh, okay, I forgot to quote the number of parameters, but we were, hundreds of thousand parameters is what we were searching over, and we would get thousands, tens of thousands of parameters in this final parameter set. So here is a slice through the data, through the parameter space for each of the libraries I'll show you. Here is when we, on the synthetic data for a crescent, and here is on the true M87 data. So you can see the green boxes are showing ones that we had determined as a good enough parameter to consider. And you can notice, like at the bottom, we get really terrible reconstructions. Just because this fits the data doesn't mean it actually can reproduce the synthetic data very well, because maybe it wants to smooth out the flux as much as possible. And we don't select things like that in the true data. And another thing that I want to highlight with this one that I think is cool is that it's kind of hard to see the labels here, but actually at the top left corner, this has no regularization in this image apart from positivity and a field of view constraint. So even this data was amazing that you could get a ring even with having just the constraint of a positivity constraint where light you're saying is positive and can't be negative, and some kind of compact field of view. Here is this for the Smiley pipeline. You can see the top set parameters highlighted in green, and for the diffmap pipeline. And then once we had these, we could do things like look at the fractional standard deviation of our results and see, are we having such a crazy deviation that this ring ever disappears? And we find that fractional standard deviation was often small. We would find a significant, sometimes, deviation around these knot regions, which we found had to do with aliasing artifacts from our beam, from the point spread function, basically. Okay, so this was, and we did a lot of tests on these top set searches, and you can look at the paper for more tests on it. But another thing we did is the validation of those gains. So remember I told you that the gains were really bad, especially for LMT. And so just in general with that calibration, with the phase, you lose pretty much, you included an absolute random phase from 0 to 2 pi. But for gains, typically, for absolute gains, typically your values are around 1 if you've calibrated reasonably well. But as I said, we didn't for LMT. So which is a telescope in Mexico. And so normally you can still weakly constrain the absolute amplitudes. You don't have to use that closure amplitudes that I talked about earlier. And if you reconstruct the images, so here is the reconstructions of M87 from the 3 pipelines. After we've reconstructed an image, we can then solve for the best gains that would best fit those images, and we plot it here. And then we did it for both M87 and a different source called 3C279, which is the AGN, where you can't see it. And you can see that the gains kind of roughly follow each other. So that gives us confidence that we are recovering the calibration at the, correctly. Another thing, though, is I told you that we could use these closure quantities to tell us about, to do the imaging. And if you, so rather than constraining the absolute amplitudes, you can just constrain these closure quantities. And if you do this, then you're completely calibration free. Like, you don't care at all what the calibration is. And we did this for the data as well. So here is on the left is the image that we get where we use closure phases, closure amplitudes, and some absolute amplitudes in the process of imaging. And here is when we absolutely did not let it ever use any calibrated data. And we still got a ring. It's not as pretty of a ring, but it still got that ring out. So that's really nice that we weren't reliant on the calibration, which people were afraid of, because if it was wrong, maybe it's leading us in a wrong local minima or something. And then a final thing that we did, and this is a very brief synopsis of this, is model fitting. So here we've made an image. That was the goal so far. But also we want to extract some parameters from these images. And we also just want to verify if we fit for instance, a very constrained model. So here we allowed every pixel to be different, but let's say we only allowed crescents or rings. You know, what best ring fits the data and things like this. This was important in model fitting. But first we just took our top set parameters that we had reconstructed, all those, couple tens of thousands of them. And for each one of them, we just mapped out, we just found through really simple algorithms what the best fit circle is, for all of them. And then from this, we plotted a histogram of what the best diameter of the ring is. And we could do this for lots of different types of parameters, for instance, the asymmetry, the contrast, all these different things. But here I'm plotting it for the diameter. And you can see across all of the methods, the diff map, smiling, EHC imaging, across all the days, they were really quite consistent with one another. So, and even though they were all independently done. So we're recovering this parameter pretty well, I think. And then we also did model fitting directly to the visibility domain. So didn't have this intermediate step of imaging and then recovering a ring, but instead just fitting directly what's the best fit crescent. So here's we did it through kind of MCMC inspired methods. This was it was a nested sampling method developed by Dom Pesci. But you can see here, this is once it's converged, what it looks like. And you can find the diameter from this. I guess it's about the same, 42 microarcseconds. So it's a different way. Basically, more constrained imaging, but where you're really directly looking at those model fitting parameters. And so the question is, what did we learn? So actually, a large part of what we did is, it's really, really nice to make an image. And it's really beautiful and amazing to see the first image of a black hole. But we also wanted to extract some science from it. And so one of the simplest things that you can extract from this image is what is the mass of the black hole. So we know the diameter of a lensed photon ring is actually, there's this very simple equation relating to it. You got this gm over distance, speed of light squared, where the m is the mass of the black hole. And this 5.2 is like a lensing factor because of the gravitational lensing makes the ring bigger. But the thing is, this is only if you are measuring that photon ring. But as I showed earlier, there's lots of kind of stuff moving around the black holes, depending on what the accretion just looks like. So you could have like the ring appear much farther out if you had a lot of like gas flowing around. So we needed to be able to figure out what the calibration parameters were. And we did this by taking a huge simulation library by people from all around the world, collected their simulations, and then we took a subset of that and we generated synthetic data from it and did all our feature extraction methods, both in the imaging domain and directly in the measurement, visibility, frequency measurement domain. Then once we had collected a diameter, we could compare with the true mass over distance value and then calibrate these two. And what we found when we did this is that no matter if we did image domain feature extraction, GRMHD, so this is model fitting directly to those simulations, or crescent model fitting, like I had showed you with that kind of MCMC style method, they all recovered the same mass of the black hole, which is about 6.5 billion solar masses. I also just want to call out a lot of, there's a number of people on all of these stages, but some of the key people who worked on this model fitting and doing this analysis. Avery Broderick and he had a lot of students too, but Paul, I'm going to point out, Dom, Farrell, and Jason. And so maybe the question you have now is, did we prove Einstein was right? And the short answer is, I say no, but we didn't prove he was wrong. So he passed another test. And so I kind of want to give you a sense of what we did, what we could rule out. So if you have a non-spinning black hole, actually which is called a Schwarzschild black hole, then you would expect a ring, a photon ring, of 5.2 times the Schwarzschild radius, which would be, and this is, okay, sorry, backing up. There are for M87, there were two measurements of what people thought that the mass of it was. It could have been anywhere between 3 and 6 or 7 billion solar masses. So there was a huge range. And the 7 billion was from stellar orbits, and then the 3 was from looking at gas. So basically, the stellar orbits said, okay, well, there has to be this much mass inside of this region, but it could have been smaller than that. But here we see, for this, I'm showing the size of for a 6.6 billion solar mass black hole from the stellar dynamics. If it's non-spinning, but if it's spinning, then actually that ring, if that black hole is spinning, that ring shrinks a little bit. And so this is the region of rings, of photon rings that would be consistent with a Kerr black hole. However, there's other, and this is if you believed it was a smaller mass black hole, like 3.5 billion solar masses. And so if you had, though, a 6.6 billion solar mass wormhole, you would expect a ring of much smaller. And if you had a naked singularity, a super spinning black hole, then you would have something that was the ring would be the size of the radius, the event horizon. And we found that the black hole that we imaged fit really exactly on this 6.6 billion solar mass measurement. And so that means that it is very consistent with the previous measurements of the stellar dynamics. And it couldn't have been this, anything, it can't possibly be a bigger one, a bigger mass black hole, I think, because that would require that you had measured something totally different in the stellar orbits. So from this, we find confirmation with the stellar dynamics model and believe, I guess it's our best way to, a scale to measure the mass of the black hole. So another question you might have is, how is this different than interstellar? And I do have one piece of trivia that my friend told me, although I haven't confirmed it, but I've heard that interstellar actually cost a lot more to make than this picture. But anyway, anyway, they mostly got it correct. It's mostly really right. Although they did take a few artistic liberties, they removed Doppler boosting. So Doppler boosting is when the gas is moving towards you, it's going to be brighter than when it's moving away from you. And I guess they didn't like how pleasing that was. But we can learn something from this, that the bottom of the black hole is moving towards us. The gas is moving towards us, sorry. And that's why we believe it is, well, there's a couple different explanations of whether it's coming from an accretion disk or a jet. But basically, we believe that this stuff on the bottom is moving towards us. And so from that, we can get what actually the spin of the black hole is, the direction of spin. Another really interesting thing, I'm going to go back. Another interesting thing is that we notice if you stack all the images together from the different days that are independently reconstructed, you can see that there's some evolution over the week. And although we didn't want to emphasize this too much in our results because we wanted to be very confident, I'll play it one more time. We wanted to be very conservative in what we said. We don't know exactly where this evolution is appearing in the image or what's causing it. We really don't know. But we know that it exists because if you look directly in the data, you can see that over from the April 6th to April 11th, in the two other days that are around there, you can see huge evolution in the closure phases, which is telling you about the structure. So we know that there is evolution, although we're not confident enough in what that is. And you can see the lines are reconstructions, so you can see that we are recovering that change in the structure. But we might be recovering it in a bad way. Okay, so we've done a lot with M87. We have the 6.5 billion solar mass black hole that we've gotten to image. But actually, a lot of people ask, how about Sagittarius Star? So Sagittarius Star is the black hole in the center of our Milky Way galaxy, and is also another target for the Event Horizon Telescope. So M87 is great. We got really lucky with M87. It could have been 3 billion solar masses and barely like a pixel that we could resolve. We got incredibly lucky. But Sagittarius Star and M87 tell us very different things. So M87, although I showed that evolution, actually it's evolved because it is so big. It's evolving very slowly on a period of 4 to 30 days, whereas Sagittarius Star has an orbital period of 4 to 30 minutes. That means that over a night, you have a massive amount of evolution, and you no longer can make the assumption that a single image can describe all the measurements that you see in a day. And so we've been developing methods to deal with this. I want to just mention briefly, this is really important for verifying the no-hair theorem, that we see this kind of evolution, because, I'm just going fast because I know I'm running out of time, but the no-hair theorem basically says the space-time around a black hole can be fully described by 3 numbers: the mass, the angular momentum, and the charge. Charge we don't believe will happen in these astrophysical black holes. And the mass, it shows up very clearly, but the angular momentum is really hard to tell from a single snapshot. But if you see the dynamics, it's much easier to see this. So we've been working on recovering videos, and how can we get videos from Sagittarius Star rather than just still images to recover this. And also looking towards the future of adding telescopes, actually talking with JPL, and how we can add dishes in space to fill up our UV coverage, our measurement space, so that we can recover really nice videos of an evolving black hole that's changing over the scales of just minutes. And so I'll just end with this, is as you're reconstructing the black, over time, as you're seeing more measurements, what the image you reconstruct looks like. And with that, I can answer questions.
Thank you. We have time for a few questions, and please keep it to the science. If anyone, yes.
You talked about the sparseness of the data.
Yeah.
How many data points were these images typically reconstructed from?
So it depended on the day, actually. So the last day and the second day had, we actually observed usually in scans. And a scan is like a 5-minute period of time that you're observing in. It's a complicated answer. So we record data, and then this data is correlated. So initially the measurements are less than a second long, and we have that throughout like the whole night, right? But actually, by doing this additional data processing that I mentioned earlier, you can coherently average this after you do some additional processing. And so we could actually end up, new methods were developed in order to do this, and we could average for an entire scan, which would be a few minutes. And so on the different days, we had different, I can go back, but we had different numbers of scans. I don't have the UV coverage here for everything, but one thing that we found was quite amazing was that, can I take off that thing? Okay. So the 11th and the 6th had the most scans. So it was like 25 or 26 times during the night. So 6 choose 2, frequency samples, and then times 26 points. But April 10th actually only had 7 scans. It was super, super sparse, and we thought, there's no way you can get an image with 7 scans, but I don't know, we got really lucky. So I think that's really nice. So anyway, there was a variety of different data. And actually, so we, in the regularized maximum likelihood, we usually use scan average data, but the clean method used 10-second average data. So depended on the method.
Other questions? Yes.
M87 is at 12 degrees. How long of the whole synthesis map can you expect to get?
Oh, you mean like outside of the, you're saying like how far,
How
angular
long
resolution?
from the time you start taking data until you really know what it's in? Is it 8 hours, 10 hours, 6
Oh.
hours?
Well, what we would do is we observe over the entire night, or however long we can observe M87.
Right.
But we also observe looking at other AGN between. So like that 3C279 that I showed you earlier, interleaved with that so we can compare things like gains and calibration parameters. Does that answer your question, or are you asking something else?
Hold it.
Mm-hmm.
M87 more than one fold.
Mm-hmm.
You could observe 24 hours.
Oh yeah, no, we can't observe.
Right. So
yeah.
What is the best you hope to get?
I don't remember exactly how long. I can look that up for you.
Probably not 12 hours.
No, because we also, I don't think we even observe it as long as we can because we're splitting it with Sagittarius Star the same night. So we would strategically change back and forth. So I don't know how much of the observing time was on M87.
I'm more interested in the time between you start and when you stop, not the gaps.
Oh, okay, so like when I observed, we would have 16-hour observing run. And we were working at 15,000 feet, so we would actually switch back and forth, and that's why I remember that. But yeah, 16 hours, I guess, continuously observing, but that doesn't mean that all that was good data, especially some sites were not able to observe very well in the daylight. So, but usually our observing one was like 12 to 16 hours a night.
That's good, thanks.
Last question? Yes.
Imaging at these kinds of angular scales seems like it could be really powerful. Are there other classes of sources that you talk about where this kind of angular resolution might be interesting?
Yeah, so we are looking at other agents. So like that 3C279, we're learning a huge amount from that. And I don't want to say too much because they're still in the process of publishing that. I think I went too far. But we look at, actually, not only is this the smallest, not only is this the first black hole image, it's the first image at this kind of wavelength. And different wavelengths tell you different things about the sources. And so we are seeing these AGN, other active galactic nuclei that we can't see that radius, that event horizon, there's a photon ring, but we can still learn about the jet and everything. And then we're also interested in if we went to space. If you go a little bit farther out, I think I had a slide here. If we could go a little bit farther out than Earth diameter orbit, you will be able to even maybe see other black holes. But right now, from what we can do on Earth, we can only see Sagittarius Star and M87, or we predict that. But if we go to orbit longer than the distance, the diameter of the Earth, we can start to see some of these other black holes potentially.
Okay, so we have a class in here, so unfortunately I have to ask. Katie will be here for many